Hi, welcome to part 3 of Module 4. Here we're talking about how you could attend to language within intensive intervention. So in this part, you're going to learn why it's really important to be precise with your mathematical language and concise. And we're also going to talk about some of the informal vocabulary that teachers often use, where we could use formal vocabulary in its place. So where are we? Here's our arrows. Let me go ahead and fill in our DBI diagram. Here we're still focused on what to do within the instructional platform. And we also may think when we're adapting intervention of being more formal or providing more explicit instruction on the language of mathematics. So remember that instructional platform. We've done a strengths and weaknesses profile. We've developed a scope and sequence. And then we have the platform where we're either using an intervention or strategy or a combination of both of those. And that helps us really start DBI. And then we monitor progress to see how well students are doing with that instructional platform. And then we may make adaptations as necessary. Now, when we're thinking about that instructional platform, I know you've already seen this upcoming slide here, but we want to be using evidence-based practices. And when I think about what's absolutely essential to include within intensive intervention in mathematics, I think about explicit instruction and multiple representations. We've already talked about those. And I also think about a focus on concise use of language. And so that's what we're talking about in this module. In the next module, we'll be talking about fluency building, problem solving, and a motivational component. So let's go ahead and get started with this concise language. You'll notice that if I look at these IES recommendations for teaching students that have math learning difficulties, we don't specifically see language listed, but if you remember back to the first part of this module where we talked about explicit instruction, concise language is absolutely essential. And I think that that's really important in reading instruction and really important in writing instruction, but it's absolutely essential in mathematics because there's a lot of math language that students have to learn. So if you are interested in this math language, I'm going to give you an additional reading to look at. So this was written by a colleague of mine, Elizabeth Hughes. I helped out with this, and then another colleague of mine, Elizabeth Stevens. We wrote this article about trying to support clear and concise math language in the math classroom. And so we have this whole idea that instead of that, you might want to say this. Now, before I give you a few examples of instead of that, you might want to say this, I want you to think about why math language is important. So I have two sets of problems from two different sets of high stakes assessments. And I want to talk a little bit about what's going on with these assessments here. So this top problem, I think, if I remember quickly, this is a 5th grade problem. So let's look at this problem, and I just want to write the vocabulary over here that might be tricky for students or that has a math background. So when we look at the first part, it says an expression is shown. So the word expression is a math vocabulary term. And students should understand what expression means. Now here with this, if they don't know what expression means, they're still probably going to be able to interpret 5/6 plus 3/12. But it's much better if they would know what expression means. So then we continue. It says, which expressions have like? So they have to understand what the word like means. And it can't mean, oh, I like something, but it means that they're similar. And then we also see the word denominators. So just in, gosh, how many is that? 2 sentences, we already see 3 mathematics vocabulary terms that students really need to know to be able to solve this problem. So then I can continue reading. That could be used as a next step to add. So there's another math term. And then after that, I see 2, not the numeral 2, but the written word form of 2. And then after that, I see fractions. Now, I have not even gotten to solve this problem yet. But there I see 1, 2, 3, 4, 5, 6 mathematics vocabulary terms that students need to interpret. And then I want to point out, we've already got it up here on the list, but they have to select the 2 correct answers. Many students would probably just skip by that and just circle one of those, not realizing that there are 2 correct answers. So this is why math vocabulary is important. To answer this question, students have to understand these different terms. And if they don't understand those terms, if teachers haven't been using them within intensive intervention, it's going to be pretty hard for a student to solve this problem. Now I'm going to go ahead and just kind of draw a line here, because I want to look at this other problem. This is a third grade problem. That's a little bit amazing to me, but let's look at the vocabulary that's supposed to be used here. I see the word expression again, all right? So that's a really an algebraic term that we're seeing used more and more down the elementary grades. Which expression is equal? So students have to understand what that word means. So 6 times 3 and y. So 6 plus 3, because the numbers are in the same order, I would say that students have to know the word same. And maybe we could even say order, understanding what that means. 6 divided by 3, because division, look at this one, I'll scoot to the side there. Division and multiplication are inverse operations. So we have the word division, you have to understand, read then understand that, multiplication, and then we have the term inverse operations. Third grade. That's where students are expected to know this term. Inverse, and I'm going to run out of space on my blackboard, operations. All right, let's look at part C, I think, because the order of the numbers does not matter, so I would probably consider numbers an important word. We've also got addition. Oh, that was up there in 5th grade, but now we're seeing it here in 3rd grade. And then finally, because the order of the numbers does not matter, in multiplication. We've actually got that word there already. But what's amazing to me is this problem, first of all, it's very word heavy, which is going to be a difficult thing for students. But look at all the language that students have to be able to understand in order to solve this problem. It's absolutely amazing. And again, this is a 3rd grade problem and a 5th grade problem. We're not talking 8th grade mathematics here, 3rd and 5th grade. Now I'm going to go ahead and push pause because I need to erase all of these words, and then I'll see you on the next slide. Unpause. Now we're going to talk about why students might have some confusion with mathematical language. First, a lot of words in mathematics are homonyms. That means that they have 2 meanings. So if I think about left, I could think about turning left, or I could think about something that's left over. When I hear the word base, I could think about sliding for first base. I could also think about the base within an exponent. Square, can think about the shape of a square. I could also think about a square, an exponent. I could think about something that's round or having to round a number. And I could think about mean. You're so mean to me versus I have to find the mean of some numbers. We also have homophones, so words that are spelled differently but have the same sounds. So some that we write into in mathematics is, oh, that's pi. I might think, I need some pie in my belly. Or I need you to find the sum. That could be confused with sum of the time. And here we have rows and rows, or 8 and 8. Now this is obvious to you if I'm talking about the number 8, or that I ate some pie, thinking about my pie right there. But it's not always obvious to students. And so we really have to think about the mathematical language and be very precise with our math language and concise. And we'll talk about that in just a minute. Now, when I talk about math language, there's really 4 types of terms that students have to know in math language. So there are technical terms, terms that students only see in mathematics. And students often have difficulty with these types of terms because they're longer and they have a technical meaning. But sometimes students do okay with these terms because they only have one meaning, and it's in mathematics. So here are some examples of technical terms: trapezoid, rhombus, numerator, addend, or subtract. We have subtechnical terms. These are terms that have 2 meanings. So here are some examples. Base, I already talked about that one. Degrees, let's think about degrees. So I could think about temperature degrees. I could think about degrees that I earn from school. I think there's another type of degrees. I can't even think about it right now, but I bet you can. When we think about cube, there are different meanings of that: a plane or an arc. Now, subtechnical terms might have a math meaning and a general meaning. So for example, degrees, I have a math meaning when I'm measuring the degrees with temperature. I also have a non-math meaning when I earn a degree from a high school or a college. Some other math terms have 2 math meanings. So when I think about cube, I can cube a number, or I might have to find the volume of geometric cube. So there's just like all kinds of ways this can be confusing. We also have symbolic terms that describe the numbers and symbols of mathematics. So not only do students have to know what the plus sign means, they have to be able to read the word plus. Students have to be able to read the word form of numbers and units. And then we have general terms. Oh, and is right here to represent the decimal point, or the break between whole numbers and rational numbers. And then we have general terms. These are terms that really are general English terms, but we see in mathematics. So we might ask what shape is above the circle? Can you measure this angle? What is your answer? Which one is longest and which one is outside the box? All of these terms here could cause confusion for students if they don't know what these terms mean. Now, there's hundreds of mathematics terms that students need to know. And so that means that teachers need to be really focused in on using the correct language and using that language in the correct way. So as I told you before, we have an additional reading if you wanted to check it out. Instead of this, say that. And I wanted to share a few examples from that. So when we're thinking about numbers and operations, teachers might say, instead of, and they might say, and the last one's 10. This happens in counting, so 7, 8, 9, and the last one's 10. That's kind of a chant or a song that many teachers will say. Well, I want you to think that there's no last number. So you cannot give me a last number. Numbers go on infinity. So instead of saying that, you might say 8, 9, 10. So don't say there's a last one. And you give students a hint. We'll stop counting there, but you could count more. And that's really important because so many students, especially young students, think that 10 is the last number, or they can stop counting at 10. And what numbers do students have the most difficulty with? 11, 12, and the teen numbers. Now, instead of saying what number is in the tens place, well, and if I'm looking at a number, in fact, I'll go ahead and write one here. Let's see, what number do I want to look at? We'll think about 374. That's the number I'm going to think about right now. What number is in the tens place? There is no number in the tens place. The number is 374. What digit is in the tens place? 7 is the digit in the tens place. When I'm reading this number, 648, should only be used when we see a decimal point or when we're talking about the break between whole numbers and rational numbers. It should not be used within whole numbers. This should be said 648. This is a thing that a lot of students do, and why do they do it? Because their teachers throw in "and" all the time within numbers. And another thing that we'll see in terms of numbers and operations, a kind of early counting, is teachers describing a bigger number and a smaller number. Now that's an informal vocabulary set of terms. Bigger refers to size, so bigger and smaller refer to size, whereas greater and less, or greater and fewer, refer to quantity. So we want to try to be mathematical when we're talking about these things in mathematics. These things are going to help students have a more precise understanding of mathematics. Those over there maybe aren't like entirely wrong, but are just a more informal way of talking about math. Now, an example that I can point out is using bigger number, smaller number. We see a lot of teachers do this in the elementary grades. But when I look at high stakes assessment items, when I look at test questions and workbooks and textbooks, they don't ask which number's bigger, which number's smaller. They ask which number's greater, which number's less. So if you're using that more formal vocabulary, students are going to have a better understanding of what you mean when you ask what is greater, what is less. Here are a few other examples of instead of. All these relate to fractions and more like rational numbers. So there are not numbers in the fraction. The fraction is one number. So if I am looking at the fraction, I'll write one of my favorite fractions up here, 3/4. This is one number. So this 3/4 is made up of 3 in the numerator and a 4 in the denominator, but 3/4 represents one quantity, one number on the number line. And in the same way, we don't have a top number and bottom number. Guess what we have? A numerator and denominator. First grade students can describe numerator and denominator if you use those vocabulary terms consistently. It is not a top number and a bottom number, and if we refer to those as such, that's why students think there are numbers in the fraction instead of the fraction is only one number. When we ask students to reduce fractions, that kind of has the idea that we are making fractions smaller. No, we are finding equivalent fractions. There's also other ways to say this. So if I have the fraction, let's say 6/12, I can find fractions equivalent to 6/12. I'm not reducing 6/12. Reducing 6/12 would indicate to me that I'm making 6/12 a smaller quantity, and that's not what we're doing. And then the same thing here with 1.29. So that would be represented here, 1.29. That is an informal way of saying this. The more formal way, or the correct way, is 1 and 29/100ths. And right there, that's where we're allowed to say our and. Not within whole numbers, but from the break between whole numbers and rational numbers. Now I have a few others instead of this say that, and I'm not sharing all of them with you today because you're going to come up with a few of them in just a few minutes. But instead of corner, you should say angle. Instead of flip, slides, and turns, you should talk about reflections, translations, and rotations. Now you might say, Sarah, woo, that's a mouthful. But when we look at how students are asked to think about transformations, it'll say which of these is a translation, which of these is a reflection. It never asks which of these is a slide, which of these is a turn. Instead of a box or ball, we should think about those as the technical terms, cube and sphere. And then we have the longhand and shorthand, which represent the minute hand and hour hand. Now I want you to fill out the chart with your own examples of instead of this, say that for each of the mathematics strands. Now, as you're thinking about the language that you use within intensive intervention, I want you to think about whether your language is precise. So whether it is actually defining the mathematics that you want to define. So examples of that would be the denominator is the number of equal parts that make the whole. So that's a precise definition of the denominator. Or I could say a difference problem is when I compare two amounts for a difference. And we'll get to that. We'll get to each of those explanations in later modules. I also want you to think that when you are providing explanations about mathematics or the steps in mathematics, is that your language is concise. So try to take out extra words, extra sentences, and that type of thing. And this is, we've talked about that within our part on explicit instruction. So here, if I was asking a student to show a fraction, I would say to show a fraction, look at the denominator. A denominator of 5 means I need to break that whole into 5 equal parts. It's a pretty concise definition of, or it's not a definition, steps of focusing on that denominator. I could also say to use partial sums. Add the hundreds, then add the tens, then add the ones, and then finally add the partial sums. Be very concise with the language I'm using so that I'm not taxing students. They don't have to wade through all of this excess language. I'm being precise with the mathematical language in terms of definitions and ways that I explain it. And then I'm being concise with the definitions that I use. So now we're going to watch this video of Stephen and Eric, and they're working on a lesson around quadrilaterals. And what's going to go on in this lesson is I want to just write all the different math vocabulary that they use during this lesson, and then we'll talk about that math vocabulary after the video plays.
Eric, so now we're going to have you build some quadrilaterals by yourself, okay?
Okay.
All right, so can you build me a parallelogram?
Got it.
Awesome. So we're going to look at this one, and so what makes this a parallelogram?
Because none of the lines ever intersect. They just keep, none of the purple lines intersect, and none of the yellow lines intersect.
So they don't cross each other, right? So they don't intersect, right?
They don't cross each other.
Good, so it's a parallelogram, and is it also a quadrilateral?
Yes.
Awesome, good job. Can you build me a rectangle?
Rectangle.
Awesome, so you built a rectangle?
Mm-hmm.
Good. So what makes this a rectangle?
Well, two things. Number one, both sides are equal. One side is longer than the other side, and also all the angles and degrees are equal sizes.
Good. So it has the same degrees for each angle, and two of the sides are shorter than the other two sides, right?
Right.
And is it also a parallelogram?
Yes, it is a parallelogram.
So what makes it a parallelogram?
Because again, none of the lines ever intersect each other.
Awesome. And is it a quadrilateral?
Yeah. Yes, it is. Four sides.
Good. Awesome. 4 sides. And lastly, or next to last, can you build me a square?
Square.
Good job. Awesome. So what makes that a square?
All the angles and degrees are equal, as well as all the sides. It's a parallelogram because the sides never intersect each other. And it's a rectangle because all the degrees and angles are the same, and a square is the special name we give to it.
Awesome. Good job. All right. So the last thing that we're going to do is, can you build me an example of a shape that's not a quadrilateral? So remember, what does a quadrilateral mean? It has
Four
what?
4 sides.
Good. So can you build me a shape that doesn't have 4 sides? Awesome. Good job. So how many sides does that shape have that you built?
5.
5. And what's the name of that?
It's an polygon.
Pentagon.
Pentagon.
Right. It's also a polygon. All right. Well, awesome job, Eric. Thank you for helping us today.
All right. All right, so that was a really interesting video, and if you're wondering kind of like why I'm staring at the screen is that I can see the video, it's kind of like past where I'm writing, so it's the easiest way for me to watch it. So I know it looks a little funny, but that's what I was doing there. But what I was also doing is trying to write down all of the math or math-like terms that Eric and Stephen were using in this lesson. So I want to just look at, just go ahead and count the number of words. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So this lesson ran about 5 minutes or so. We have 22 math or math-like terms used in this lesson. Now I wrote, when I say math-like, so not is not, we wouldn't consider it really a math term, but when he asked, show me something that's not a quadrilateral, you really have to understand what not means in order to show what is not a quadrilateral. Now, some of these terms are those technical terms, so terms that only have a meaning in mathematics. So, for example, quadrilaterals, parallelogram, rectangle, when we talk about pentagon and polygon there at the end, those are technical terms. But we also have a lot of what I would consider, well, what are considered sub-technical terms. So here I see square, there's degrees, we already talked about that. Sides has a more general meaning and a mathematical meaning. Same thing with angles. Oh, I wrote sides, oh, and sizes, yeah. So we've got sub-technical terms. We have some symbolic terms here that Stephen used, 2 and 4. We've got 5 over here. That would be another sub-technical term that Eric would have to interpret. And then we have general terms. So I would say shorter and longer, a little bit more general terms, but used in mathematics. Never and not are definitely terms, but they were used in a mathematical way. So lots of different words here, and if Eric had a difficulty understanding the word rectangle and degrees or shape and not, it would be more difficult to handle this lesson. Now, when we were thinking about language that was precise, Stephen was providing some pretty precise definitions of these quadrilaterals. There was one thing that he did that you might have caught where he did talk about rectangles as having two parallel sides that were shorter and two longer sides. A lot of people think that's true with rectangles. It doesn't necessarily have to be true. They just have to have two sets of parallel sides. But he was really good with talking about what is a quadrilateral. It's a shape with four sides. So he was very precise with his definitions. The other thing about Stephen, and this is kind of just how he is as a teacher, but I think it's meaningful on how he teaches, is he is concise with his language. He only says as much as the student requires. And one of the nice things about him is that he said, oh, I now want you to make me a rectangle. He gives lots of quiet time for Eric. So he's not saying, good job. Oh, I like how you use that yellow thing. And a lot of teachers like to fill the dead space that they're kind of uncomfortable with silence. Stephen does a really nice job of being concise. I'd like you to make me a rectangle. Then he asks questions. What makes this a rectangle? So he's not really filling the void with extra words that Eric doesn't really need. So he did a really, really nice job with this lesson. But you can see in just a 5-minute clip all of the language that's used within mathematics. And we have to think about, are we making that language precise for students? And are we making that language concise? So I'm going to go ahead and tell you about the next workbook activity. I'll go ahead and put it up here, but the words are kind of over there. So please ignore that because you can read this in your activity. You're going to look at a lesson on word problem solving. So this is an intensive intervention lesson. It is an evidence-based intervention. And I want you to identify 5 instances where the math language is precise and identify 5 instances where the mathematical language is concise. So precise means that we're very specific with the definitions that we're providing about something. And concise means that we're using just the minimum number of words to be able to explain a concept or procedure. So in this part of the module, we've been talking about how can you attend to math language within intensive intervention. And here I wanted you to understand why formal mathematics language is important, why we need to use the word expression, why we need to use the word parallelogram. And then I want you to think about planning for your math language to be precise and planning for your math language to be concise. So now as you do your discussion board, I would like you to think about all the stuff that we've talked about in this part. And I would like you to share 3 examples of, instead of this, say that with your classmates.